So I'm back. I might be stumbling through this today because I'm a little tired and I haven't looked at this since Thursday or whatever. Um, we actually had done 34.1. 34 is an easy one. It's pretty straightforward. Most of these require some little trick. Like 31 is an easy one. 31.1 is pretty trivial. And then, if I recall, I think he did 31.2 just by induction. I would have thought there was some sort of trick to that. 32 and 33, it's like, I guess if you look at the right-hand side and you want to come up with a series that would have that as a coefficient, as like your typical binomial coefficient. That's like a hint at it. This is basically, like 32, it is just basically a square of your typical series that you might expand with a binomial theorem. But for some reason, when I first saw that, I was like, well, how am I going to deal with the cross terms? But you're looking specifically at the nth coefficient. So all of the cross terms, well, it's not a trick, but like the cross terms end up being like n0 and n, and n1 and n minus 1, and n2 and n minus 2. So like they all happen to be equal, and that's why you're getting squares. That's for that particular coefficient. And then anyway, like I was saying, 34 is really pretty trivial. That's just what happens when you multiply two series together. So he's telling you that this would be the formula for the product. And then if you have factorials in your denominator and you have factorial in your product, then you get a different formula that involves the binomial coefficients. Kind of looks like the binomial theorem again. And 34.1 did involve a trick. So 34.1 is where we ended last time. Like, I was just staring at it and I wasn't sure how to do it. But it's really easy if you sort of realize it's coming from this second definition, and you could just multiply by e to the x. Your alphas would be 1 in that case, right? So I probably shouldn't bring it up again because we talked about it last time, and I don't want to make this video too long today. But at the very end, I had gotten confused, and there's really no reason to. It's pretty straightforward. So it's saying if your bn's are defined like this, the sort of alternating series with binomial coefficients of some given a's. First of all, another way to phrase this hypothesis is like, suppose you had a series like it's going to write just bn, x to the n. But now that I think about it, you probably want it to be, like bn over n factorial x to the n, right? And we'll let ax be the same thing, something like this, right? Starting at 0, and it doesn't actually have to stop. It can just go off to infinity, I suppose, right? For a particular one, for bn in particular, it's a finite sum, but the series is not necessarily finite. Anyway, So if you use this terminology, you can also use the e to the x function, which is just 1 over, right? So by 34.0, when you multiply two series that have a factorial on the bottom like that, like for instance e to the x, your gamma value is going to be given by this formula, which is conveniently almost exactly what they gave us here, except for the alternating bit. Okay, so yeah, it's not. Here's another way to express how the BNs are defined. I think this is his first step. Is he's like, well, if there was an alternating term in addition to your actually, I guess I must have this backwards, huh? Let's put an A here, AK. Like Z to the K. Oops. Let's do Z, since I just switched it up. Then this would give you a new number on the right, which is really just 1 times this, yeah, with the binomial coefficients in between. So we could put over here like B sub K, K factorial, C to the K. And that would define the BNs. Like we know from 34, we have BN is the product of whatever this is. Of course, it's 1. Let me pull that up again. But it's just, alpha 0 BN plus, then you get this binomial expansion type of thing for the coefficients. And it changes in a pretty predictable way, right? So the sum is always n. So here you might have 1 times and then this thing at 0, which I guess would just be a0. And then you get a negative sign for the first guy, right? -1 to the 1, a1, and that's times 1. Like the coefficient from this E series is always just going to be a 1, so it's not really doing anything interesting there. And I forgot it already that there's supposed to be a term here, right? So if you're doing this in n, you should have an n choose 1 right there, okay? It really just follows from the first part, along with the extra factorials. So when you multiply by one of the factorials, it kind of becomes this formula, n factorial over 1 factorial times n minus 1 factorial. So it just follows from the Cn part. So yeah, we're getting stuff like this, etc. So -1 to the n choose n, I guess an, and then you're getting whatever this guy is, but it's a 1 all the time, so it's not super interesting. So that was the hypothesis. Like if Bn is defined this way, then you want to show that An is also basically defined that way. Like you're going to get B0 minus N1 B1 up to -1 to the n choose n Bn. Like show that happens. But so this was the whole trick, is like defining B in this manner using this product makes it really easy. For some reason I was like, I still don't get it, and I was trying to multiply by e to the -z, which is almost the right direction. You can basically just replace z with negative, like take this almost as an identity, because that's the definition of the BNs, right? Replace z with -z. And you'll get e to the -z on this side, but we're going to move it over here. So you'll have e to the -z times the sum, -1, ak, and I'll put a -z here, okay? So the negatives are going to cancel, and you're just getting, and this still equals on this side, but now it's got this alternating bit, right? Because we replaced it with negative z instead of z. So if you move the e to the z to the right side now, you've got exactly what you wanted. Okay, and on the left, these two canceled, so you actually just get ak on its own. And that is exactly what we were trying to show, that if this happens, then it sort of happens going the other direction as well with the bn's. So now your ak is given by this alternating formula that we jotted down a second ago. You know, very much like the bn was defined in terms of the an's a moment ago, or the ak's I should say. The an is defined in terms of the bk's in the same exact manner. So it's really kind of a trivial change. Once you notice this trick of multiplying by the series e to the z, anyway, we saw that last time. So what I wanted to do today, I have done 35, but I didn't do 36. Like, it's just over my head. I'm going to read the explanation. I don't think I'm going to even try it. I'm just going to try to understand it. And I haven't done any of the other ones, so it would have been smart for me to prepare. Like, 40 looks familiar to me, but I don't remember where I would have seen it. The other ones don't really look familiar. This one's interesting. You get this harmonic sum. Yeah, I'm not familiar with that one either. So I have not seen any of these before. Oh, sorry, my gain is way up. I haven't seen any of these. Probably be smart of me to prepare for the next video, but then, I don't know. Maybe it's less interesting. Anyway, I did do 35 at some point. I think he does it in a more clever way than I do. I don't remember what he does, but he does something really, he just makes some observation that makes it fast. I didn't do it that way. I think you can do 35 with induction. So that is what I had done. So let's take a look at 35. He defines this new operator, x to the n given h. And it's very much just your typical factorial thing, except that instead of going down by 1, we're going down by h. Okay, so we take n factors where you decrease by h every time. Right? Here'd be a 0 factor, a 1 factor, 0 through n minus 1. So you get n total factors of things that decrease by the amount h. And then he tells you you have this identity, which is basically just the binomial theorem again, but with this new operator. So that's wild. Like, basically the binomial theorem holds even if you had redefined factorials to not be by integers, but by any real number h. So that's impressive. So the way I did this was I just noticed, like, first of all, x to the, like, well, I guess, for instance, x to the 1 given h is an x. Okay. And then yeah, I'm looking at 35. And then I started, like, probably playing with what this would be to different powers. So, like, of course, one of them is just itself, like we just said. But how do you get from 1 to 2? Like, what is 2 given h? I guess it's like itself times x plus y minus h. So you can kind of group this minus h term with either one, whichever it's more convenient for you to do, you know? What we're supposed to be observing is that you get this binomial. Well, first of all, notice that it's true for 1. This is the case of n equal 1. notice that you're getting x to the 1 h plus y to the 1 h. So it was true just for n equals 1 case. For 2, though, I'm multiplying by this thing. Like, of course, we're going to distribute, but let's see. Yeah, there's an extra y, right? Like, we can group the h with whichever variable it's convenient for you at the time, So like one time this hits against x, and it's probably going to be convenient for me to take x minus h, right? So one thing you get is x times x minus h plus y, and then the other one you get is y times like that. You get both of those terms. This term right here looks like x to the, not 1h, but I guess 2h, right? Plus y 1h, and then here I've got, oh, wait a minute, that's not true. That's y1h times x. So it's like x to the 1h times y to the 1h. And then over here I've got y to the 1h, x to the 1h, plus our y 2h. So it seems like it worked. N is 2 in this case, and we're getting, sort of 2 choose 0 plus 2 choose 1 times this term. So it obviously worked for n equals 2 as well. And then here we got 2 choose 2. So I figured, it took me a minute, but I did it by induction the other day. After I noticed that this happened, I was like, well, it probably happens in general. So if you knew that it happened for n minus 1, could you get there? Like, could you take n minus 1 h and multiply by x plus y minus, I guess it would really be this, right? And do you get, like, basically show that you get the formula for x plus y to the nh. Okay? Our n choose k as k goes from 0 to n of x to the I suppose it would be, you could go either direction. Let's do n minus k given h times y to the k given h, right? So I'd be looking to show that this occurs if you know that it happens for this factor, proof by induction. So I was trying to do induction on n. That's what I would do on this. That's just because, like, again, I noticed that it happened. Like, I noticed that it fell out for the case of 2 in kind of a cute way where I could, like, group them. So I was like, well, it probably can't be that bad to do it by induction. So here we're assuming that it's true for this case. I mean, I already saw that it's true for 1 and 2. But now we're assuming that it's true for n minus 1. Knowing that this part can be expressed as a sum of n choose k, x to the n minus k h, y to the k h, as k goes from 0 to n. And then we're going to multiply this by the next term, the last factor, I should say. in your definition of this little creature. So yeah, again, this would be n terms. That would be the last factor. There's, I should say, n factors, starting at just x plus y minus 0h, x plus y minus a single h, times da 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 da, down to this x plus y minus n minus 1 h's. So my goal would be show that this equals this, or in other words, now that we know that this left, if you believe this left-hand side is given by this formula, does this times this factor equal this right-hand side? So show that this equals this right-hand side. Did I screw this up already? I did, right? Because because this is not n minus 1. So let's change this to do it correctly. That might make your life a little easier. This top part is not an n, it's supposed to be an n minus 1. So this is x to the n minus 1 minus k given h. See, I told you I was tired. Anyway, this would be the n minus 1 case. And now we're able to I'm thinking, of course we want to replace this with n choose k somehow, but we do know that n choose k is the same as n minus 1. You can do this with it, which we had just shown back in number 31. A few different ways to believe that. You can't even see what I'm writing anymore. So yeah, I would probably expand this, right? So we get two different, like the left-hand side, I haven't done anything yet. I'm about to replace this n minus 1 choose k with probably like this minus that was my instinct, you know? But I might be wrong. I don't, you know. That's what I chose to do. This has not changed. This is still n minus 1. And then this is our left-hand side. I'm still trying to multiply this whole thing by this one term. So I'm claiming that that's going to work out for you. Like, if we do this out, it'll somehow equal this stuff. Looks like the 0 term here is going to be meaningless. Like, one of these will drop out. But then when you get to... I was going to say we want to reindex this second term. First term, maybe we'll just remove that 0th term. Here, let me pause for a sec. All right, back. So, if you're just popping in, this has been kind of a sloppy start. But it's kind of a cool problem. I wonder what wonder what other because he doesn't seem to be using this thing anywhere. I wonder if this has any applications. This operator. Yeah, I don't see him using it. But yeah, let me recap since I need to rewrite this anyway. So yeah, the question is, he's defined this new operator. It's a lot like a factorial, but instead of being decreasing by 1 on every factor, you're decreasing by h, just a real number h. So if you have n terms, that means it looks like this, right? And then we're going to have n of these terms, like that. One thing I noticed right away was that if you let n be 1, you'll just get x back. And then what he's asking us to show is that you basically have the binomial theorem again. If you were to expand this under this definition, it works out to be this stuff. So like the sum of the first argument is always n, just like with exponents, the sum is always n in the binomial theorem. And other than that, you get binomial coefficients as well. So we're trying to show that x plus y raised to this, this operator will actually give you, I realize it's right here, I don't need to think about it, but yeah, the first term is like n given h, and then you get n choose 1, and then this goes down by 1, and you've got a single y there. Oops, that's an h, damn it. Anyway, you get the idea. X to the n minus 2, h, y to the 2, h, all the way up to n, choose n. I guess this one will be y to the n, h, and x to the 0, h, which would be 1. 1 times nothing, 1 times 1. So show that this happens. And I noticed that it happens sort of obviously for 1. I mean, it happens like this is x to the 1h plus y to the 1h. So I noticed that it happens for n equals 1 case. That it even, like if you multiply this guy by x plus y minus h, it'll group either direction. So it works for, it's true for n equal 1 and n equal 2. I don't know why I'm writing this out again for you, but so for instance, this would be I mean, it's this by definition, right? But when you expand that, you get x1h times y. Yeah, I was saying a moment ago that you can group it different ways. Like when you multiply by this term, you can group the x with x minus h, and you can group the y with y minus h, and so that formula does kind of naturally pop out. So like when you do this, this is just the n equal 2 case, like my base case for induction here. When you do this, you can group the x with x minus h, and you can group the y with y minus h. So you're getting